Hello, my name is Jeremiah Foster and I'm Genevi's Community Manager. I'd like to talk to you today about the Genevi Google Summer of Code project for 2018. This year's project, a next-generation voice command system, was Genevi's second participation in the Google Summer of Code. The Google Summer of Code program is a global program focused on introducing students to open source software development. Students work on a 3-month programming project with an open source organization, such as Genevi, during their break from university. The program is vitally important in a number of ways, such as providing projects like Genevi a new contributor, who hopefully will continue to participate after the Google Summer of Code is over. That has been the case in our case this year, with the student going above and beyond what would be considered successful completion of the project. In addition, since the Google Summer of Code is geared towards open source, all the artifacts and code from the project are available in Genevi's GitHub and Wiki. This year's participants were led by Genevi's technical lead, Gunnar Anderson, along with myself and the student, Chandeepa Dissanayake. The project was proposed by Genevi, but the technology choices were up to the student. With a background in machine learning and neural networks, Chandeepa chose to capture audio input to the system, turn the audio into text, run the text through a pre-built model for recognition, then return the recognized text as a command. This was just one of the possible scenarios that the voice control could be used for, but it was found to be a likely use case. Another use case that was implemented was playing a song whose title was entered by the user via voice. At a high level, the voice control code implements commands on Genevi's in-vehicle infotainment platform. The process for building up that command from input from the user is described in this slide from the Mozilla Foundation. The series of steps highlighted show the steps we used, with an additional step, namely transforming speech into text. As we can see, the neural network on the right is being trained in this illustration. A similar pipeline was used in our implementation. Still, the illustration is useful to show how the voice command is processed, even after the model is built, since the process is identical. In a closer look at the functionality and the technical details, we can see that a pipeline is created, which contains each of the steps. Step 1, capturing speech input via a microphone. Step 2, transforming speech into text. Step 3, text recognition via a deep neural network. And finally, Step 4, processing the resulting commands on target. In Step 1, Chandeepa and I continued to use common off-the-shelf hardware, with Chandeepa using a headset to capture speech and myself using a Jabra Speak plugged directly into a USB port of a Raspberry Pi 3. The software created then captures the spoken text via the microphone and performs speech recognition, converting the audio data to its textual representation. Then that audio data is sent to Google's speech-to-text API, which would return back the textual representation. If useful speech is not found in that audio data, an error will be thrown by Google APIs, which is handled by notifying the user. One can, of course, use any API to do speech-to-text, but this was the one that was chosen for this project. We used the Google Text-to-Speech API together with a third-party library, but also looked at technology from Mozilla. The goal was to be agnostic to where the pre-trained model resided, and to use the technology to complete the project in the time allotted. In Step 2, we saw that we used Google's Cloud API to turn speech into text. In Step 3, that text is interpreted by a pre-trained model. The textual representation of the audio data received from Step 2 is mapped onto the model. The underlying meaning or gist of the user's speech is refined and converted to a task or function in the IVI system. A good pre-trained model contains a wide variety of different phrases through which the user can execute the IVI commands. Neural network model training requires lots of data to be effective, as well as ample computing power, which is one of the reasons why a pre-built model was used. Training such a model for in-vehicle infotainment uses is an interesting exercise in and of itself, but too large an undertaking for our project. Nonetheless, the ideas behind building a suitable model were addressed, and the computational approach was discussed in the project. This knowledge will likely be helpful, even if a different API or an SDK is used. The final step is executing the task as interpreted by the model. In our case, a wrapper function was written in Python to execute the task or function by interacting with the IVI system directly. It also was designed to handle errors and to queue the user. Here's an example of the project in use.
Initialization successful. Waiting for commands.
Find me the city of California.
Please wait while we look for the location for you. We have several locations identified. Let me list them down for you. First one is San Leandro. Second one is City of California. Which one did you mean?
The second one?
Sure. I will open that up for you.
Play Justin by Andrew Applepie.
We are searching for the song. Please wait. We found the song you've requested. Let's listen.